Okay, here's the other part of the topic 5 worksheet. We're just going to continue the topic of zeros and polynomials. Problem 5, we want to find a polynomial function of degree 3 whose zeros are -4, which has multiplicity 2, and 5, which has multiplicity 1. And then we're going to write our answer in a polynomial form. Now, polynomial form just means that you're adding up a bunch of terms, and we're going to want our form to be in this form that we see here. Okay, so degree 3 means that the highest power of x that we see should be 3. Now they're telling us the zeros, and remember, if k is a 0, x minus k is a factor. So -4 is a 0, which means that x minus -4 or x plus 4 would be a factor. Now -4 is a 0 of multiplicity 2. So that would mean that its factor would be seen twice. 5 is also a 0, so x minus 5 would be a corresponding factor. This has a multiplicity of 1, so its factor is only going to be seen once. At this point, we're all set up in a factored form here, and we would just simplify to give our answer in a polynomial form. X plus 4 times x plus 4, when you FOIL that, would be x squared, and then 4x and 4x would be 8x in the middle. 4 times 4 is 16 at the end, times x minus 5. At this point, you'll want to distribute x into these three terms, and then distribute -5 into these three terms, and then collect your like terms. So x times x squared is x cubed, x times 8x is 8x squared, x times 16 is 16x, and then -5 times x squared is a -5x squared, -5 times 8x is -40x, and then -5 times 16 is a -80 there at the end. Combine the like terms, and we end up getting this result here, which would be our degree 3 polynomial, and also our answer that we're looking for. I mentioned on the other video, pay attention to how the book wants the answers written. Sometimes they want it left in a factored form, and sometimes they want it left in a polynomial form. Okay, they'll tell you that in the directions what form they want the answer to be written in. Problem 6, we're supposed to find all the zeros for each polynomial function. In part A, now I do have a polynomial, although this is conveniently set up in a factored form, because I can just simply set the factors equal to 0, right? I want to find the zeros, so I'm looking for the numbers that are going to return 0. Therefore, it makes sense to set the function equal to 0 and solve for x. You can set the individual factors equal to 0. X plus 7 equals 0 means that x is -7. Now that's going to have a multiplicity of 2 because the factor was seen twice. 5x minus 2 equals 0 means that when you add 2 and divide by 5, you're going to have x equal 2/5. And then x squared plus 4 equals 0, subtract 4, and then take the square root of both sides, and you're going to have plus or minus 2i. We want to find all the zeros, so I want to make sure that I'm including all the numbers, whether they're real or imaginary. Okay, part B is also where I want to find these zeros here. Now, the fundamental theorem of algebra tells us that we can just simply look at the degree of the polynomial and know how many zeros there will be. So knowing that I've got a degree 3 polynomial here means that I can know right away I'm going to have 3 zeros. The plan for this problem is to use factor by grouping. So if we let the first two terms be one group and the last two terms be a second group, 9x squared would be in common to the two terms in the first group. I can factor that out. That's going to leave me with x plus 3. And to have the factor by grouping method work, I'm going to need another x plus 3 coming from group 2. Well, I can get that if I factor out a -2 from these last two terms here. That'll leave me with an x plus 3. x plus 3 is now in common to these two groups, so we can factor that out of the whole thing. 9x squared is left from group 1, minus 2 is left from group 2, and when you set these two expressions equal to 0 now and solve, x equal negative 3, that would be one answer. 9x squared minus 2 equals 0 when you add 2 and divide by 9, and then take the square root of both sides. The square root of 9 is 3. Of course, don't forget about the plus or minus there. Plus or minus root 2 over 3 would be the other two zeros. All three of these are multiplicity 1, and we only indicate a multiplicity when it's not 1. Otherwise it's understood that it just occurred one time. So the three zeros here are negative 3, root 2 over 3, and then negative root 2 over 3. And we're just leaving everything in exact form as usual here. Okay, problem 7. A polynomial function of degree 4 has zeros negative root 3, and 5 plus 6i. Find the remaining 0. Okay, so I know that there's going to be 4 zeros here. They've told me 3 out of the 4. I just got to get the remaining one. For this problem, you want to be using the conjugate zeros theorem. The conjugate zeros theorem said that if a plus b times I is a 0 for a function, a minus b times I will also be a 0. So all I need to do here is I just need to take the conjugate of 5 plus 6i, that would be 5 minus 6i, and you're done. Problem 7 to me is just a go right to the answer type deal by using the conjugate zeros theorem. Okay, problem 8. We want to factor the polynomial function given that k equal negative 6 is a 0 of f of x. And then we're going to use the factors to find all the other zeros. Okay, well, since negative 6 is a 0, that means that when I plug in negative 6, I get 0 in return. Now, the plan here is going to be to factor, although we're not going to use factor by grouping like we did here, because no matter what we do with the groups, we're not going to have a common factor in each group like we did on this last problem. So now this is still going to be a factoring situation, okay? Knowing that negative 6 is a 0 means that x plus 6 would be a factor. To continue factoring, I want to divide. I want to take the function and divide by x plus 6. Since you're dividing by a binomial, you can use synthetic division. And negative 6 is the 0 of the denominator, so that's going to go in the upper left-hand corner. There's a negative 1 in front of x cubed, a 10 in front of x squared, a 19 in front of x, and the negative 30 at the end. So we're all set up here to divide. Bring the 1 down. 1 times negative 6 is negative 6. Add the next column, you get 4. 4 times negative 6 is negative 24. Add the next column, you get negative 5. Negative 5 times negative 6 is 30. Add the last column, and you get 0. Now 0 is the remainder, which really shouldn't surprise us that we got 0 as a remainder here. Like, we already knew that negative 6 was a 0 of f. If we were getting any other number, not 0, there would have been a mistake going on in this division process. Now, I'm more interested in what's to the left of 0 here, because when we divide, we see that we get 1 times x squared plus 4 times x minus 5. And with this equation, if we multiply both sides by x plus 6, that'll clear out the fractional form for us. And we're going to have x cubed plus 10x squared minus 19x minus 30 on the left. That's what we're calling f of x. And then on the right, we'll have x plus 6 times x squared plus 4x minus 5. So like I said early on here, we are going to factor, and you can see that we've already started to factor f of x. X squared plus 4x minus 5 is going to factor further as x plus 5 times x minus 1. So now that I have this in a complete factored form, I can set the factors equal to 0. X plus 6 equals 0 means that x is negative 6. That's a number that they told me is one of the answers. X plus 5 equals 0 means that x is negative 5, and x minus 1 equals 0 means that x is 1. Okay, problem 9 is the last problem here. It says to consider the function f of x that's given there, and we want to use the rational zeros theorem to list the possible rational zeros of f. Now, for this problem, like if we were to find the zeros, which I'm not going to do, but if we were to find the zeros, there would be 4 of them, and we have no idea what these 4 numbers look like, okay? They could be nasty numbers that would be very difficult to get by guessing and checking. Notice how like they did not give us a k value here like they did in the last problem. And really in that last problem, they did us a huge favor because they kind of helped us get started with the problem. Okay, some books don't do that where they give you the k value there to help you get started. So, in order to start this problem, I would have to guess and check. And what we're doing is we're going to create a list of possible zeros that would be fractions, and if the zero is a fraction, it's going to be on the list. Now, the fraction is going to be in the form p over q. P is all the factors of the last coefficient, which for us is a 9, and q is all the factors of the first coefficient, which for us is a 2. Make sure that you get those correct. I'll have students accidentally flip p and q. Don't do that. Okay? So to get the p values, I want to list all the factors of 9. 1 and negative 1 are factors of any number. 3 goes into 9 evenly, along with negative 3. And by the way, if a number is a factor, its opposite is also going to be there. So you're going to have plus minus for all this stuff. 9 is a factor of itself, along with negative 9. And so it looks like there are 6 factors of 9 that we have listed here. Now get the q values. We want to list all the factors of 2. 1 and negative 1 go into any number. 2 is a factor of itself, and also negative 2 goes into 2. So we're going to have what would be 4 factors of 2. Now that we've identified the p and q values, we want to list all the possible rational zeros. So I'm listing all the numbers in the form p over q. And to begin, why don't I start by listing all the fractions where 1 or negative 1 would be in the denominator. If you have plus or minus 1 divided by plus or minus 1, that would be plus or minus 1. Plus or minus 3 divided by plus or minus 1 is plus or minus 3. Plus or minus 9 divided by plus or minus 1 is plus or minus 9. Okay, so now move on to if 2 or negative 2 happens to be in the denominator. Plus or minus 1 divided by plus or minus 2 is plus or minus 1/2. Plus or minus 3 divided by plus or minus 2 is plus or minus 3/2. And plus or minus 9 divided by plus or minus 2 would be plus or minus 9/2. So it looks like we have 12 possible rational zeros. And again, if I were to find the zeros here, I know there'd be 4. And to begin the guessing and checking procedure, like it would make the most sense to begin guessing numbers that are on this list. If I were guessing like 5, I would be wasting my time because 5 did not come up on this list. Okay, so we are basically drastically reducing the amount of guessing and checking required to start the calculation without this k value given to us initially. And that's really the power of the rational zeros theorem. Okay, and at this point we're now done with the topic worksheet.